Welcome everyone. Today we're going to start to see like a quick application of our partial derivatives, right? And so kind of again, taking it back to 20A, when we did our derivative, the big application that we started with was finding that equation for a tangent line. So now with multiple variables, when we start to see those functions of several variables that give us a surface in 3 dimensions, now we're going to, instead of talking about just a simple tangent line, we'll get into our tangent planes. Okay, so let's get into that discussion. Let me share my doc cam and we'll get going. All right, so getting going here, right? So like I mentioned, back in Calc 1, 20A, here at MPC, right? We dealt with those equations for tangent lines. Okay, and so we would see in 2 dimensions our Cartesian coordinate system here, my function f of x or y is equal to f of x. We can have our set point a, b, or x naught, y naught, right? And then through that point, we would create our tangent line, right, intersecting at that one point alone on our curve. And then our tangent line, we can rewrite y is equal to, right, m subtangent, or f prime at a, right? There's my derivative of my function at that particular x coordinate. Okay, times x plus b, that generic, I'll put capital B, y-intercept, and I should be better about y minus b underscore point, there we go, equals that f prime of a times x minus a. There we go, that's a little bit better, my point slope form, which we can take and transition into that format, the slope intercept form. But there we go. This is really what I wanted to focus on. There we go. And so for any point on a curve, we can find our derivative, the slope of that tangent line, right? And then building that point slope form. Okay. In 2 dimensions, right, there's only kind of one direction, one way of viewing that tangent line. So now what we have to concern ourselves with, right? So now for Calc 3, right, our Math 20C, the tangent lines at a point on our surface can truly go in any direction. And so now, excuse my drawing here, but let's think about it. Here's our 3-dimensional coordinate system. Let's say now we have this surface, okay? Or we can draw a paraboloid, ellipsoid, something like that, right? But we have the surface in 3 dimensions. So now for some point, we choose in our domain space, we run that through, we evaluate our function there. We get that point on our surface, x naught, y naught, comma, z naught, right? But then with the work we had talked about with our partial derivatives, we can imagine, right, depending on what derivative we're taking, that as we start to look, we can get these kind of tangent lines. Maybe we're going that direction, right? If we're holding the x constant, we can have this tangent line in that y direction, for instance. Or maybe we're going this way, we can have a tangent line in the x direction. Hold the y constant, right? Or any other direction, as long as I pass from that point. Maybe I'm going at an angle, right? We can get a tangent line in any direction. And that's what we're going to talk about later. We start getting into directional derivatives, right? Instead of just facing purely in that y direction, purely in the x direction. What if we're at some angle, if you will, going across that surface at an angle, up that mountain, down that valley, whatever it is, right? And what slopes are we feeling there? What slope is experiencing, right? So in this case, we talked about evaluating the partial derivative of the function to see in particular that holding y constant, how is that x changing? Holding x constant, how's the y changing, right? We talked about those. But when we're just kind of sitting on that surface and we talk about, okay, we want to be tangent, we want to kind of take a line, take the slope. Really, it does kind of depend on where we are, but we can also accommodate, depending on where we're facing, all these different possibilities for tangent lines, right? So with that in mind, to incorporate all these possible tangent lines, we will create a tangent plane. Okay, so this plane now, that's going to encompass, it's going to incorporate, it's going to include all of the possible tangent lines at that particular point. Okay, so instead of just having, and now let me do it this way, we redraw this slightly. Okay, so here's our surface again. Here's some point on our surface. And we'll do some more labeling as we go along. But now what we're going to kind of identify is that now here, we're going to create this tangent plane. And that tangent plane is going to include, it's going to have as part of it, all those different possible tangent lines at that particular point. Okay, and so if I borrow, I should say, this little sheet here. Okay, this, I guess, right? So imagine my hand here. Let me stop sharing for a second. Let's see if this view helps. Okay, so like imagine my surface, or even let's take my mouse, right? Let's say my mouse body. There's my surface, 3 dimensions. Okay, so if I'm at some point here, okay, at the little cursor, or at the D from the old school Dell mouse, right? I'm at that point, right? Depending on which way we're looking, either the tangent line can be kind of sloping down the mouse. I can be going upwards, climbing up a little bit where it's arced, right? So this would be a tangent line. That would be another tangent line, right? Still just intersecting at that one point on my surface, but I can go in any direction. So to incorporate all those different lines, the different directions I can go, instead we'll create a tangent plane. So I can set where this plane intersects at that one singular point. I know it's kind of weird to see there, but it's going to include all those different tangent lines in all those different directions. Okay, and again, I know doing this online visually, I haven't perfected getting those demonstrations, but hopefully with what I've drawn, that little demonstration suffices. All right. There we go. Back to my .cam. So now looking at this, as I just mentioned, right, the tangent plane will include, it will have as part of it, right, all possible tangent lines at the specified point. On our surface. Okay, and if our surface is given by z is equal to f of xy, we'll have that point x naught, y naught, z naught, right? Running x naught, y naught, those fixed points. Back in 2D, we call it A and B, right? Plugging those in. All right. So then, recall, think back. In chapter 12, we had discussed it, right, from our text. The equation for a plane, in general, a times x minus x naught plus b times y minus y naught plus c times z minus z naught was equal to 0. And we can use our algebra skills, rearrange, get ax plus by plus cz is equal to some constant, right? But looking at that, well, we have our point on our surface that we're talking about. The piece that we're missing, A, B, and C, right? We would have our normal vector to the plane. By those values, right? That's that vector that's going to be perpendicular to any vector on the plane, right? And here, our normal vector will be perpendicular, right? Orthogonal, another way of saying it, right? From that right angle to any vector, or in our case, line, right? Having a direction vector for the line in the plane, right? So that means if this tangent plane is going to is going to include, right? It's going to possess all those tangent lines. The normal vector that we need for our equation of the tangent plane is actually going to be perpendicular to all of those tangent lines. It's kind of an interesting feat, okay? But thinking about what we did, especially with that quiz we had done, okay? Thinking about that, let's go through some of our work and finding that, okay? So with that in mind, taking this away, let's construct our equation then for the tangent plane. And notice I've kept this all general. I haven't looked at a specific example yet, but this will work for any of those surfaces, okay? where we have z as a function of x and y. Okay, so if we have that, right, we have our point on the plane, or on the surface, sorry, given by z equals f of xy, x naught, y naught, z naught, right? So generalizing here, just so I have some reference to use. All right, here we are. So as we mentioned before, right, we can think about having these tangent lines in different directions, right? So for instance, my tangent line in the y or x direction, let's do x direction, just go alphabetically, okay? All right, so that means we're going to hold y constant. Right, so depending on where we are at the x naught, y naught, sending that up to our surface here. If I was thinking about that tangent line in the x direction holding y constant, right? Thinking about that tangent line in that x direction, I'll just put 1 there. That tangent line, if I think about this in our parametric form, it's going to be my x naught plus a times t, right? Some direction, we'll bring that back in just a second. Y naught plus, and now if y is holding constant, I'm not going to change in the y direction. It stays y sub 0 along the entire path. And then for that z naught, how is that changing? Well, that's exactly where that partial derivative information comes in. Because when we held y constant and found that derivative, that z sub x, f sub x, that partial derivative, okay, in the x direction holding y constant is exactly that slope. Is if I was to hold y constant and walk along that surface, what would I be experiencing? It's a positive slope, negative slope at that point in the x direction. So this is exactly my f sub x at that particular point. I know I should include that, but just notation wise, there. So exactly that partial derivative is exactly that direction value for the tangent line for the z component. When the y is being constant, x is varying, that partial derivative is exactly that component. And x is just traveling on its way, so we're going to use a 1 there, right? Depending on how much value we're using for t, right? That's that increment of stepping that we're doing, right? That's how much x changes. Okay, so that one might take a little thought, but we're kind of centralizing that. Okay, we're letting everything happen in the x direction, so we'll normalize, right? We'll just kind of make that our unit, and then everything else based on that component. Okay, and so in that case, my direction vector for this 1, 0, f sub x, my partial derivative with respect to x. And so then extending that, now if I hold the x constant and I go in the y direction, let me call this T2, this is T1, okay. If I think about that in the y direction, holding x constant this time, what does that equation look like? Well, again, thinking about that parametric form, starting at that same point on our surface, pushing this up. Now, if I'm holding x constant, x is not changing, 0 for that direction. If we're doing everything in the y direction, kind of, or let's say normalized, right? Everything is based on there, so that's like single unit. And now let's see how we change that z direction, kind of like we talked about with that x direction, f sub y now. So that my direction number for that line, tangent line, 0, 1, f sub y, right? And so then to finish up, taking for granted what we had talked about here, right? On my discussion up top then, when I want to kind of create then this tangent plane, it has to include those two tangent lines and any other tangent line. So we're going to need a normal vector from those two, right? So my normal vector for my tangent plane that's going to be the cross product of these two direction vectors for my two tangent lines in that plane. Okay, so that's how we're creating, just like we did in chapter 12 in our work with vectors and whatnot previously. The equation for a plane, we're using that information right here. So for the normal vector, that v1 cross v2, what's that going to look like? Our direction vector for the first tangent line, 1, 0, f sub x, partial of f with respect to x. The second, 0, 1, f sub y. And now going through our calculation, okay? So here comes our 3x3 determinant calculation. Our direction unit, our unit direction vectors up at the top row. That first direction vector 1, 0, f sub x. The last row, the second direction vector 0, 1, f sub y. In computing, remember we're doing those cross products, right? Keep track of those incorporated signs. That's a j plus that component for k. There we go. All right. So now in computing for I, cross out that column, that row, 0 minus 1 times f sub x, minus for j, f sub y minus 0 for k, 1 minus 0. 1 minus 0, okay? So in this case, my normal vector, 0 minus f sub x, negative f sub x, like partial of f with respect to x for the I, minus, that's why I'm going to put minus f sub y for the j, and then plus 1 for the k. All right. Or negative f sub x, negative f sub y, and positive 1. So there's my normal vector. So going back to it then, our equation of the tangent plane right? Our surface z was equal to f of xy. Our point on that plane that we're talking about, x naught, y naught, z naught, okay? Taking the components into play, okay? So here's our A, B, C. There's our point straight from it. So in this case, we're going to get negative f sub x, x minus, I'll put it in green, I guess, x naught, plus b, which was negative f sub y, that partial of f with respect to y minus y naught, plus c, 1, z minus z naught is equal to 0, okay? And then now with some rearranging, like that 1, shoot that through that parenthesis. These negatives, let's add those to the other side. So in this case, we're getting that z minus z naught. I guess I should let that green, sorry. But over here, f sub x times x minus x naught plus, right, adding these two to the other side. There we go. And for these partial derivatives, these are evaluated, computed at x naught, y naught, right? They're not general expressions. These are constants in our equation, right? So that means for the f of x, it should really be like f of x of x naught, y naught, f of y of or at x naught, y naught, right? Get constants, get real results for those. These are not variable expressions, okay? So for any surface, we can create this equation for our tangent plane by using those partial derivatives, okay? I'll leave it there for that information. I can write up an example going through it and provide that with our written notes, okay? All right, crew. Take care. If any questions, please let me know.